You have Chapter 8, Section 2 formula. We had ordered pairs, we had arrow diagrams, we had charts. I would like some more organized fashions by which I can represent a given relation. So there are two main versions closely related to our diagrams and to our charts, but let's start with a matrix. A relational matrix or a relation matrix, MR, is an array. Now, if we have a set and we are looking at a relation on the set A, A has a certain number of elements, whatever the cardinality of A is, call it N for the moment. Then I have a set of ordered pairs consisting of elements here. So if I have an element, xy, then in my array, I will put a 1 in the spot where row matches the x and column matches the y. So the array in question defines the rows by the element of our domain and the columns by the element of our range. So if we had a relation from one set to another, this would still work. Here's a relation from the set 1, 2, 3 to the set 1, 2. And I want you to include only numbers, ordered pairs, where A is larger than B. My array is going to have 3 rows. And it's going to have 2 columns. A row for the numbers 1, 2, and 3, columns for the number 1 and 2. And in each entry here, 6 total numbers, you either put a 1 or a 0. You put a 1 if it's in there. You put a 0 if it isn't. This spot corresponds to the ordered pair 1, 1. Does it satisfy this relationship, yes or no? In each of these ordered pairs, it's the row number followed by the column number. So it's an RC entry, row, column. So AB, is A bigger than B? Then I put a 1 here. Is A bigger than B? I put a 1, yes. I put a 0, no. And I can go through now and I can do all of these. What's my second column look like? That is correct. This time, instead of going from A to B, I'm going from A to itself. A relation on A goes from A to itself. You should be able to come up with a 3 by 3 matrix, 3 rows, 3 columns, that describes this relation. What is the matrix for this relation? If it helps, write out all 9 of the ordered pairs, A, comma, B, and then see which ones satisfy our equation and which ones don't. I wrote it B bigger than or equal to A, but that's the same as writing A less than or equal to B. So the row number needs to be less than or equal to the column number. Row 1, column 1, yes. Row 1, column 2, yes. Row 1, column 3, yes. Row 2, column 1, no. Row 2, column 2, yes. Row 2, column 3, yes. 3, 1, 3 is not less than 1. 3 is not less than 2, but 3 is less than or equal to 3. There's the matrix for this relation. Please note that if my relation goes from one set to another, then the number of rows and the number of columns may be different. But if my relation goes from a set to itself, the number of rows and the number of columns must be the same. We call a matrix like that a square matrix. I wrote A is square. I realized A is a set. My matrix is named M. Sorry, wrong class. In the linear class, I do a lot of matrices named A. Sorry about that. Questions? We had a bunch of properties about relations. Can I tell from looking at a matrix about properties? Now remember, the properties we were looking at was when our relation, things like reflexive and symmetric and transitive and anti-symmetric, we had all those things we defined on Monday. What was the definition of reflexive? A relation was reflexive if what? We wrote it down Monday. At least you should have written it down Monday. I wrote it down Monday.
A R A for all A and E.
In our set.
Yeah.
For all A belonging to our, for everything, it has to be related to itself. But wait a minute, that means that all the ordered pairs like this are in my set. What does that tell you about the matrix that we're going to get? What do I know has to have a 1 in it? What do I know has to have a 0? What can I not tell about? Where can you guarantee me you're going to put a 1? Say again? Well, that would mean everything is related to everything. Reflexive only tells me that A is related to itself. Yes? So when the row number and the column number are the same, so I know I'm going to get a 1 in the first row in the first column. I know I'm going to get a 1 in the second row in the second column. In the third row in the third column, marching all the way down here to the bottom row, all the way on the right. I don't know anything else about this, but I know that every number down that one diagonal line must be a 1. Now, when we talk about the entries in a matrix, we talk about the row number and the column number, right? So I can index the entries in a matrix by using a subscript, not just a single number, a pair of numbers. I'm going to call the IJ entry is the thing in our matrix in row I and column J. It's always row, column. This is a religious institution, right? Roman Catholic, Roman Catholic, RC. I know where I am. I can keep track of this. Maybe you're an atheist, fine. It's RC Cola. I don't care. Remember it somehow. Row, column every time. Row, column. The diagonal is where the row number and the column number match. So MII is 1 when R is reflexive. That main diagonal, going from all the way in the upper left corner, all the way in the bottom right, must all be 1s. So I can go back to the relation we were doing earlier. Is this one reflexive? Yes. 1 is related to 1, 2 is related to 2, 3 is related to 3. Even if I didn't know what this relation was, and somebody just gave me the matrix and said, is this relation reflexive? I can answer that. Other properties, we had symmetric. How do I know if a relation is symmetric? And that's got to be true for every pair, right? So here's a matrix for the relation. Let's suppose that we have a symmetric relation. Somebody give me a row number and a column number. Row 3, column 2. In that spot, do you want to put a 1 or a 0? Let's put a 0 there. That means the third element is not related to the second one. A3 is not related to A2. So tell me, what do you know about that spot? In the second row, in the third column. It also has to be a 0. Because what that does is that switches the positions, right? And if this was a 1, then the other one has to be a 1 as well. Aha. Whatever happens in the IJ position has to be the same thing happening in the JI. Here, let's go down to, I don't know, the last row in the first column. If that's a 1, then way up here in the last column of the first row, there also has to be a 1. Because what this says is that AN is related to A1. If that's true, then A1 has to be related to AN. Wherever I see a row that's got a 1 in it, whatever column, I have to be able to switch to the other number. So if I'm in the first row, I have to look down in the first column. If I'm looking in the second row, I have to look down in the second column. I have to see the physical manifestation of these numbers matching, no matter what row or what column I'm in. MIJ must match with MJI. And that actually means that our matrix itself has symmetry. And it's symmetry that relates to our reflexive idea. Notice I am folding from the upper right to the lower left. Or I'm folding from the lower left to the upper right to say that those things match. What's the line I'm folding along? The diagonal we were talking about before. So we talk about the matrix being symmetric across the diagonal. If you know anything about matrix operations or anything about matrix algebra, this is about the transpose of a matrix. So we could equally write that the transpose of this matrix is the same as the original. There's a transpose function in Excel. You might have done it in one of the data classes. Questions? What was our third property? Anti-symmetry. What was the definition for this one? If ARB and BRA then, okay, wait a second. ARB means I get a 1. Those two things are related. BRA means I get a 1. Those two things are related. But these have to be entries that match up like these, yes? And this says if you have a 1 there and a 1 there, then A and B have to be the same? What the? The I number and the J number, suppose they're different. We're in a different row than we are a column. Like here, we're in the 3rd row, 2nd column. If there's a 1 there and there's a 1 here, that's a problem, isn't it? Because that would say that the 3rd row and the 2nd row need to be the same, and 3rd and 2nd are not the same. So that means we can never have both of those be 1 at the same time. Ever. You could have one of them or the other, but not both. I've heard that phrase before. You can have one or the other, but not both. Chapter 1, people. That's exactly what it is. That's an exclusive or. At most, one of those is a 1. They could both be 0. Could they? Could they both be 0? If they're both 0, then this is false and this is false. False arrow something. Uh-oh, that's a true statement. They can't both be false either. That means for every pair across that diagonal, one of them's a 1, one of them's a 0. So this property only applies to the things that are not along the diagonal. So it applies only to the other pieces, right? Just like symmetry really only cared about the stuff that was not along the diagonal. But in symmetry, we wanted those two things to be the same. Now I see why they call it anti-symmetry, because the two things have to be different. Every piece that's up here has to be the opposite of the piece that's down here. Is this relation symmetric? No, because what's above the diagonal does not match what's below the diagonal. Is it anti-symmetric? Yes, because everything that is above the diagonal is the opposite of what is below the diagonal. They're exactly opposite each other. Now I understand why they called it what they called it. From the definition, it looked really weird, but now, from the matrix, that seems to make a lot more sense. Seems to. Might just be me, I don't know. Questions? There was another property. The last property we talked about on Monday. Transitive.
So A and B are related, and if B and C are related, then A and C are
Ew. Ew, 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 ew. I don't like that. It is possible to do this from the matrix, but the way in which we do this from a matrix requires me to discuss something else. These are ones and zeros. But I just made use of a logic idea, the exclusive OR, yes? So what if we treated the ones and zeros like they were trues and falses? Then I could use logical operations on a matrix. Here are two matrices. Before I go any further, are either of these matrices reflexive or symmetric or anti-symmetric? Clearly, this one is not reflexive. There are zeros along the diagonal. Same thing here. There's a 1 here, there's a 0 there. There's a 0 here, there's a 1 here. There's a 1 here, there's a 0 here. These are that one is anti-symmetric. What about the other one? Now, see, this is 1 and 0, but this one's 1 and 1. So it's not anti-symmetric and it's not symmetric. It doesn't match above and below. It isn't the opposite above and below. The only property that's true is that that first one is anti-symmetric. I want to take these two matrices and treat these as logics. So a 1 is a true and a 0 is a false. Well, that means I could take these two matrices and put them together. With an OR. And all that means is that in each and every spot, I take the thing in the first matrix or the thing in the second matrix. Now, because the people who did matrix and relations didn't spend a lot of time talking to the people who did logic and logic symbols, they called this something different, which annoys the fuck out of me. It's an OR. I should call it an OR. But the people who do relations call this a join. Has to do with something about filters and filter spaces, and I don't understand it very much. I've just barely touched it in all of the classes I took. So I'm just gonna run with it. I call it an OR, and they can lump it. So let's do this OR. What goes in the first row in the first entry? First row, second entry.
0.
Third entry. Second row, 1.
1. 1.
Aha, all ones in that thing. How about the bottom row?
1. 1. 0.
Now remember, I said that relations were sets, and that meant that we could do things on sets. Well, this turns out to be the matrix for the union of those two relations. Because you're either in the first one or you're in the second one. Isn't that what a union is? A union's an OR statement. All ties back together. If I can do unions, I can do intersections. That means I can do and instead of or. And again, for some godforsaken reason, they call this the meet. M-E-E-T, not M-E-A-T, the meet. of my two relations. Well, that's an and that's going to be the matrix for the intersection of my two relations. What is this matrix? Read it to me going across the top, left to right, top to bottom.
0, 1, 0, 0, 0, 0, 0, 0.
The only time I get a 1 is when they're both ones. Everything else, at least one of the two is a 0. Okay. Transitive. To do transitive, I need to multiply these matrices together. How many of you know how to multiply a matrix? It's been a long time, right? Unless you've taken linear algebra, you probably haven't done a lot of matrix multiplication. But I need to do it using ands and ors. So what I'm going to do is I'm going to say notice this time it's the same matrix. What you do is you pick a row and a column. So pick a row, pick a column. What row, one column?
1.
Okay, so we're going to do row 1 and column 1. And the answer to what I am going to do goes in the row 1, column 1 spot. So what I do is I take the first row and the first column, and I do 1 and 1, first entry, or 0, 1, or 1, 0. Multiply by doing the and, multiply by doing the and, multiply by doing the and then add by doing the or. Hey, those were the words we used in the counting setup and in the probability setup, right? Whenever I saw the word and, I multiplied. Whenever I saw the word or, I added. I'm doing exactly that. I have to do this 9 times. Every row and every column together to get 9 different things. This is called a Boolean product of matrices. And it appears in our textbook on page 182, which unfortunately for us is in a section I didn't do, which is why we're not going to spend that much time on it. This is the entirety of what you will do. You'll do this once. That's it. You'll never see it again. So if I did the second column, it would go down the second column. And the first row, second column answer would go there. In the first row, in the second column, in my answer. See, this is row 1, column 2. So I do row 1 with column 2. Then I'll do this one. That's row 1, column 3. And then I'll do the second row 3 times. And the third, that's why I have to do this stupid thing 9 times. And the bigger my matrix gets, the more of a pain in the neck this is. Which is why this is an algorithm that can be automated and matrix multiplication can be done on our calculators. When I multiply a matrix by itself, that's squaring it, right? Something squared. A relation is transitive if the matrix of the square has non-zero entries where the original matrix had non-zero entries. This is not easy. So I think it would be nicer if there was another way we could look at transitive behavior. But to do that means I have to change gears completely. So I'm going to leave matrices behind right at the moment. Questions before I dive into a new idea? A digraph, a directed graph. For those of you who are taking it, next semester's graph theory course is going to start here. A digraph is a picture of a bunch of dots where each dot represents one of the things in our relation, one of the things in our set, and we connect things that are related. So each element in my set becomes a node, a dot with a label on it. And then, if A is related to B, place an arrow from the node for A to the node for B. This sounds psychotic. It's a picture. We did this relation already. We even drew a different kind of picture for this relation. We drew an arrow diagram for this picture, for this relation on Monday. I'm going to draw a digraph. So what I need is a node for each of these numbers. You can put these nodes anywhere you want. I'm just going to make a square. Those are my nodes. They're labeled so I know which node represents which dot. You could color code them. You could make them the actual physical letters. You don't even need the little circles. That's up to you. But now, tell me what numbers are related by this relationship. 1. Go back to Monday's notes. Does 1 divide 1? Does 1 divide 2? Does 1 divide... Answer the questions. Oh, 1 does divide 2. 1 divides 3. 1 divides 4. 1 also divides 1, right? I have an arrow from 1 to 1. How about 2? What does 2 divide? 2 and 4. So there needs to be an arrow from 2 to 2, and there needs to be an arrow from 2 to 4. Now, I've deliberately drawn that around so that I don't cross my arrows. This isn't Ghostbusters. I don't care if you cross the streams or not. It's just prettier to be that way. And that's a personal habit of mine. It only works sometimes. How about 3? What arrows are coming out of 3? Just to itself. And 4? Same deal. Is this relation reflexive? how would I know from the picture whether or not this is reflexive? And we have an arrow going from 1 to 1, from 2 to 2, from 3 to 3, from 4. We have a loop at every node. How would I know if it's symmetric? If it's symmetric, whenever you have an arrow going from one to the other, from A to B, you also have to have an arrow going from B to A. In other words, there should be no one-way streets. If you can get from point A to point B, you should be able to go directly back from point B to point A. What about anti-symmetric? I'm going from A to B. I can't go from B to A, right? I can only have one of those. I have to have one for every pair of different letters. There has to be a way to get between any pair. I don't know which way you're going to go. You're going to go from A to B, or you're going to go from B to A. But you can't do both, and you can't do neither. Transitive. Well, transitive means if I go from A to B and I go from B to C, then I should go from A to C, right? That means I should be able to make triangles. I can go from 1 to 2. I can go from 2 to 4. I can go directly from 1 to 4. There's a triangle. And that triangle has to have the correct direction. I have to go from A to B, from B to C. I have to go from A to C. Notice this arrow goes down from 1 to 4. Transitive is usually easier from a picture than it is from the matrix, because doing that logical Boolean product is not short by hand. In a computer, a matrix representation for a relation is much, much faster. Because then we'd be going from C to A, not from A to C. We'd be going the wrong way. So I have to have the correct direction in that last edge. There's a reason I like reflexive, symmetric, and transitive. That's what we will discuss on Friday. If you came in late, please come give me your assignment and come pick up the one I have for you. I will see you all on Friday.